Welcome. My name is Fred Cohen, and I'm going to discuss the Webster CyberLab architecture. This is the outline of the presentation. We're going to talk about what the CyberLab is and why it exists and the overall architecture, and then go into some particulars that'll be useful to people that want to access it. And then we're going to have a detailed discussion after we turn off the recording. The CyberLab is a facility that we created to support global research and education. Webster is a global university, maybe the first really global university, as opposed to just having a couple of little teeny campuses here and there. Webster has real campuses in real places, and lots of them. And the notion of doing science and education in a field that's science or engineering without having laboratories, it's something that can't really work. So the question then is, how are you going to have laboratories and laboratory experiments for students? And there are sort of two choices. One of them is you replicate everything and end up with 100 laboratory facilities that do all these things, which is very expensive, time-consuming, and hard to maintain, and also difficult to do securely, especially for the sorts of things we're going to do. Or do you create a relatively smaller number of them so you have enough redundancy to assure that everything continues to operate, while also limiting the time and effort and costs associated with those facilities. So the approach that we're taking is this group of not centralized, but centers, so distributed centers. And the key properties that we're trying to achieve are, we want to make sure it's safe to do experiments that would be dangerous to do on the internet or at home, okay? So that includes distributed denial of service, writing, examining, messing with computer viruses, experiments with things like emanations and covert channels. The problem there, for example, is if we're doing a Wi-Fi experiment that could break into other Wi-Fis, it could break into real Wi-Fis, and then we'd be doing bad things. So the next thing is that it has to be scientifically valid. That is, we're not necessarily trying to teach people, how to administer a Windows computer securely. We're more interested in having repeatable, testable results that demonstrate the scientific principles so that the students will know, not just for tomorrow, but for the rest of their careers. They'll understand the principles and the issues and how they work and how to do science and understand what's necessary to do engineering. And then the other thing is, would like to have it be efficient compared to the alternatives. That is, building 100 of these things all over the world. So the overall architecture, by the way, what you're seeing along the way here is pictures of the current CyberLab. This is a rack that we have that's operating within my corporate infrastructure. I have a company called Management Analytics. So within there, we have some CyberLab machines, and it's running in a co-location in a level 3, 4, somewhere between level 3 and 4 secured facility. It has uninterruptible power and 100 megabit per second direct connectivity to the core of the internet and so forth. So that's an example of a co-location. The overall architecture, we have distributed redundant locations. Currently, we're in California and Idaho. Charles is on the line, and he's in Idaho. Before long, however long is, we're hoping that we're also going to have a primary and a secondary location somewhere in the European Union, maybe one in Africa, maybe one in China, and other places around the globe. Tom thinks China's unlikely, and that's all right. But wherever we have them, the idea is that you need to have them reasonably close to the students in order to have high performance interaction. Trying to run halfway around the world for scientific experiments in real time is more difficult than it might seem, at least with today's technology. And there is this thing called the speed of light that's inherently limiting. Of course, this will follow the rollout of the programs. We can't just spend arbitrary amounts of money building a global infrastructure. We have to build students and education around the world, and as we build the educational program, the infrastructure to support it has to follow. It's redundant in some sense, but not fully redundant. For example, the Idaho laboratory that does emanations and covert channels, this is a special purpose laboratory. And it's expensive to create and difficult to do, and you need people that really know what they're doing. So we're not likely to reproduce that anywhere around the world. That's going to be a unique environment that students and faculty and researchers can access to do their experiments wherever it may be. California, that's configured as standard execution nodes for the laboratory. So we should be able to reproduce that anywhere we want. It's a fairly standard setup. We have pretty good automation for creating another one if we want to. It's extensible, so it's done in a set of modules, so we can add modules to it for relatively low cost per module as we need more performance or other similar capabilities. And other sites may have other special purpose labs, and we'll talk about that at some point. It is modular, as I mentioned. The idea is to design once and implement many times, use standard operating environments and configurations, standard access methods and controls, and hopefully support it for less cost, and hopefully over time have it supported by students who, as part of their educational process, like any other engineering or science program, they get involved in helping to make things work and make them better. The Emanations Lab is a very good example of the specialized facility. This picture you see on the left here is from the lab, and it's a little bit unclear, but if you see, this is a non-closed version of it. There's metal around it, and Charles can detail how we're trying to reduce electromagnetic emanations. And there are different shells, so they're visually isolated from each other. And then we're going to be adding insulation from sound and variable insulation from sound, electromagnetics, and light between areas. So that, for example, you can try and produce sound that you listen to on another computer in the lab, use that sound as a covert channel between machines, and then control the sound and see, how many machines you need to generate more sound or what kind of sound and how you have to listen to it in order to have an effective covert channel through that kind of barrier. So you'll be able to do scientific experiments that users will be able to create covert channels and emanations, observe them, induce noise, create separation and change the parameters of the separation and the noise, and measure the results and try and figure out channel bandwidth that they can get. So the idea here, of course, is it's safe from spillage, so we won't accidentally screw up other routers in the neighborhood. It can be tested, theorized. You can make, identify an equation for how it might work and test the equation and measure it to within some granularity. Integration and management's another issue. The dispersed facilities, makes it a potential management problem. We are planning to have tunnels, cryptographically secured tunnels from area to area, so that it appears when you're in one location as if you're in the other location at the same virtual place in the structure. So that, for example, over time, as we build this on a global basis, you'll be able to create an emulated global network in the secured environment that will not be able to deny services to anybody else or leak viruses to anybody else, but still allow you to do experiments emulating a global network. Right now, 2, sometimes 3 part-time lab managers, 1 lab director, part-time, that's me. We have tools in place for standard deployments. The documentation is extensive and being evolved over time. We have about a 65-page architectural document. We're moving to these videos as the methodology for documentation. So you'll see this video as an example of people that want to learn about the CyberLab and how it works. Ultimately, as I said, we want students to participate in the management as part of their learning experience. And we want as much self-service as feasible because, frankly, we don't want lab managers to spend their time serving requests. We'd like professors to say, let this student into this lab or not. Have students say, give me this time slot to do my experiments or something like that, rather than us trying to manage it manually. Some particulars. This, by the way, is what the wiring looks like between the machines in the CyberLab. Not as neat and clean as you might like it, but the different colored wires are from different connections to different networks, and that's how the separation mechanisms are enforced. Access, well, let me just give you an architectural picture. It's a zoned architecture. We have the internet. From the internet, you go through an access control mechanism, and then there are zones, the control zone, the trusted zone, and the restricted zone. The CyberLab exists in the trusted zone of the outlying architecture. So the CyberLab is in the trusted zone. And it has outside, inside, and compute. You can see that in the picture down at the bottom. So what happens here is the outside is intended to protect the cyber lab from the world. The inside is intended to protect the world from the cyber lab. And the compute or execution nodes are where you can do things that would otherwise be dangerous. So you can basically do anything you want to mess those things up, and it won't damage the world. And at the same time, the world won't be able to come in and cause us to be unable to do our work. And that's the intent and the design. The details of how it works, they're still being worked out, but to give you a sense, starting at the outside, you come in through a proxy. That proxies, well, lab managers can come directly to the outside machine or proxy to the inside machine. Students and professors get proxied from outside to inside to the compute node. Once they're in the compute node, they have a limited function menu that allows them to set up an experiment. So you come in and you're part of, class 23, and in class 23 you're allowed to perform experiment 5. So you say, I want to do experiment 5, and it'll have a menu for experiment 5, and it'll let you do things. For example, create me 5 virtual machines in a LAN suitable for experiment 5, and it'll do that. Then on the inside, each user that's simultaneously present gets their own virtual machine. Right now, those virtual machines have about a gigabyte of RAM. They share 2 terabytes or 4 terabytes of disk space. They have the capacity to run multiple virtual machines, and they're hopefully going to be running on their own processor. So it's a multi-processing in hardware, so that say 6 students or groups of students simultaneously will have essentially their own processor with lots of memory and the ability to run virtual machines inside it. The experiment will configure and operate the virtual machines, and they'll be able to go into the virtual machines and do things, including, they'll be logged in as super user or root on those virtual machines, so they can do anything that anybody could do. And it doesn't matter what they do on those machines, because at the end of the experiment, we can reboot it, digitally without having to touch anything. And the outside compute node continues to operate. When they leave the virtual machine, they come back to the menus. And then when they log out, the virtual machine goes away, and the next person's virtual machine can pop up. Why is it so complicated? It's complicated because we're trying to make sure that the world is safe from us and we're safe from the world. And it turns out that's not so simple to do. It includes a variety of things. So, for example, the outside limits outbound traffic to only authorized encrypted traffic into authorized compute nodes and lab manager control channels. The inside provides internal deceptions. So, for example, if you want to emulate the internet or have a DNS server that's used by the students, that's provided by the inside machine, so it can provide those services to the experimental environment. But it also limits the outbound traffic, so the only traffic outbound can be returns from the encrypted sessions inbound. So, whatever happens inside, we're not trying to prevent one of our legitimate users from, doing damage to the world from their computer. We're trying to prevent them from using our computers to go do damage to the world from our computers. Right? So as long as it's in that enveloped environment, it should be safe in terms of doing harm to the outside world. An example, a virus or a DDoS tries to attack an external site, or use some commercial virus or some commercial is the wrong word, some virus that's free floating out in the world that wants to call home to go get some other software. Well, it won't be able to call home, but the deception may allow us to provide a fake place for it to call, so we can watch the behavior that it performs. There is no actual outbound path or routable address to exit. There's no way out except the way you came in. And it can't affect the performance of any outside machine because it's in a physically isolated LAN. It's not sharing a LAN. It's not in a virtual LAN. It's in a physical network environment that's isolated through this protective mechanism from anything else. Of course, all this is transparent to the user. We inform you so that you know what's going on, but in truth, what happens is every user will get a URL. They'll go there. It'll provide them with the means to say, here's my identity, and here's what I'm trying to do. So, for example, I'm trying to get to class 15, and my name is Joe, or in this case, class ABC 23, and they'll get back a command line that will work for them in this case. In this particular instance, to get to that facility, That particular user on this particular day from that particular place issues this command and they get there. And tomorrow it might be different, right? So it varies over time. So for example, a student in one class can't tell the student in the next class to use this, or Tom identified, what if a student shares this information with other people so they can come into the lab? Of course, we can't stop them from doing that. On the other hand, if they only have so many hours of time slots in the lab, they're not going to get their lab done if they give it away to somebody else. And of course, at the end of the semester or whenever the authorization changes, they're not going to be able to hand that over to the next person. And of course, the user, when they log in with whatever the authorized method is, maybe it'll be an SSL session to a web server, it depends on the particular function. The user will have a menu that lets them set up the experiment, provide the parameters. They start the experiment. Depending on what the experiment is, they have to go do it. And they end the experiment. When it finishes, they're logged out and their virtual machine is made available for others to use and cleared. So with that, I'm going to end our presentation and welcome your questions and turn off the recording. So